Hello, everyone. This is Sean. Welcome back to HFR. We're picking back up on part 3 of our AC circuits discussion. And we're going to continue on looking at purely inductive and purely capacitive circuits, and then kind of mix up different concepts into more discussions. Now, I'm going to be honest with you. A lot of the pictures and stuff that I've pulled for this teaching series was out of brainkart.com. That is BRAINKART.com. Because I wanted to include pictures like I have in the previous presentations, and they just seem to have the better selection of what I was looking for. But I did back up a lot of what I was reading off of that website with my own basic electronics books and stuff that I've used over the years in college and etc. When I learned fundamentals of electrical engineering and fundamentals of electronic principles myself. That being said, we are coming back to our steady state analysis of AC circuits. And the first thing we're going to look at here is an AC circuit containing pure inductance only. Now, by pure inductive coil, that is this coil you're seeing right here at the top, we mean a coil that has no ohmic resistance and hence no I square R loss. Whenever an alternative voltage or alternating voltage is applied to a pure inductive coil, a back EMF, electromagnetic force, is produced due to the self-inductance of the coil. Now, this back EMF will oppose the rise or fall of current through the coil, as there's no ohmic voltage drop. The applied voltage has to overcome this self-induced EMF only. And when I pictured this in my head, I just kind of think of like, well, as an AC voltage is rising, right, it's eventually going to fall. And so we're seeing how one polarity and the other polarity of our alternating voltage is kind of at work against itself with the verbiage I present to you concerning back EMF. Now, our formulas are, no different than what we learned in our previous set of instructions. I do want to mention one commonality we will find in our discussion here is also found in DC motors, wherein the coil of a motor is turned, a magnetic flux changes through the coil, and an EMF is induced. Now, Lenz's law tells us the EMF opposes any change, so that the input EMF that powers a DC motor is opposed to the motor's self-generated EMF or back EMF. Although I am getting a bit ahead of myself in this lesson, what I really desire for you to know is, if you can recall how we calculated voltage from our previous video, is we can also determine the back EMF of a given inductive circuit as well. Now, back EMF is calculated using the formula you see in the middle of our circuit on the left. That is this formula you see right here. As there is no ohmic voltage drop, the applied voltage has to overcome this self-induced EMF only. So if the back EMF is E, that is this little symbol we see here, then we can say that E equals L times delta I over delta T. It can be further expressed as you see in our equation near A. Then we can, with integrating both sides, we get the equation expressed down here in B. Now, if you take notice, V plus E equals O, so we're saying no ohmic value, right? You essentially are saying V and E are equal to each other. So look at our equation. Here goes our voltage, V sine alpha T. You can see how that's been swapped in, and we've moved some things aside to integrate both sides to get our sine and our cosine for the equation. Now, moving on in our theory, in case of an AC circuit containing pure inductance only, the current lags behind the applied voltage by an angle of pi divided by 2, or 90 degrees. And the power factor of the circuit is lagging. So power, and then here goes our current. We see that, again, current lags behind the applied voltage. So we have our voltage first, and then we have our current. Okay, it's coming in later. You got to think of this as a period over time. If this represents 0 seconds, then over here is, just because I'm off the top of my head, I'll just say 90 seconds later, right? But regardless, that's not correct at all, but that's primarily there to give you a picture. I'm digressing though. Perhaps simply we can remember a purely inductive circuit as current lags voltage by 90 degrees. Okay, just keep that in mind. In a purely inductive circuit, current lags voltage by 90 degrees. Now, one final thing I've not mentioned in a purely inductive circuit is inductive reactance, or XL, as you see over in the right-hand corner here. Inductive reactance is the resistance offered by the inductor and measured in ohms. Yes, every inductor in an ideal world would have a 0 resistance, but we know that is not actually the case. Inductors do, because they are a coil essentially wrapped around a metallic core, like a ferrite core or something along those lines. Inductive reactance varies directly with frequency. I want you to keep that in mind. For a steady state current where frequency equals 0, our inductive reactance, or XL, will equal 0. Thus, an ideal inductor offers no resistance, as I previously stated, and as we learned when we studied steady DC current in our DC circuit series. However, this will not be the case when we are dealing with an alternating current. Recall, inductors pass DC, but block AC. You probably recall me mentioning that in the past, and if I didn't, I'm mentioning it now. Now, let's say we have a 400 microhenry coil connected to an AC circuit in which an effective current of 6 milliamps is flowing. We can find out the voltage across the coil if the frequency is 1000 hertz using the formula found here over in A. So we have our inductive reactance, and here's our formula. We're taking those values and we're multiplying them out. We get our ohmage, we get how much impedance we have here, okay, or ohms. And then we plug it into our previous voltage equation, and we get our volts RMS. Pretty simple things. Now, I also want to mention AC circuits containing pure capacitance only. Okay, there's not much really to talk about concerning a purely capacitive circuit. I mean, just the same with a purely resistive AC circuit and a purely inductive AC circuit. You're probably hard pressed to find a circuit like that. Okay, in common electronics, regardless. But however, we should at least be familiar with the instantaneous charge on a capacitor, where in Q, what you see down here, is the instantaneous charge on the capacitor. The EMF across the capacitor at the instant Q divided by C, according to Kirchhoff's law rule. So we have a formula for that, as well as our instantaneous value of current, or I, as we see over here, as expressed in the equation on the right. So 2 more formulas that we add to the mix when we're dealing with a purely capacitive circuit, AC circuit, that is. However, the main thing I want you to take away from this is we got something that occurs that is basically the inverse of what occurred in a purely inductive circuit. Oh, I forgot to change something here. Capacitive. capacitive. Forgive my mistake right there. In case of an AC circuit containing pure capacitance only, the current leads. Look at this. We see the inverse. The current leads the applied voltage by angle of pi divided by 2 or 90 degrees. And the power factor of the circuit is leading. Okay? Perhaps simply to remember a capacitive circuit as current leads voltage by 90 degrees. So we just swap what we previously stated concerning our purely inductive circuit. Now, one final thing that I have not mentioned in a capacitive circuit, purely capacitive AC circuit, is capacitive reactance, which is this XC that we have here, and you'll see over here on the right as well. Okay, capacitive reactance is the resistance offered by the capacitor, and it's also measured in ohms. Capacitive reactance varies inversely with the frequency. So again, we have something that is basically the inverse of what we stated for a purely inductive circuit. Now, for a steady current where frequency equals 0, again, our capacitive reactance, or XC, will also equal 0. Thus, a capacitive circuit offers infinite resistance to the steady current, so that the steady current cannot flow through the capacitor. And if we recall what I said back in our DC series, remember, capacitors block DC, but pass AC. Again, the polar opposite of inductors. Let's take an example wherein a capacitor that is 10 squared over pi microfarad is connected across a 220 volt 50 hertz AC mains line. We can calculate that. Over on the right, you see the example. We can calculate the capacitive reactance of those components within that circuit and produce an RMS value of current and write down the equation of voltage and current as seen on the right hand side, indicated by our letter A. So I'll give you a second here to look at that and pause the video. So if you want to test this out for yourself, it's not incredibly hard equations there at all. All right. Again, this is just our fundamentals. Okay. Keep in mind, you will most likely never come across a purely resistive, capacitive, or inductive AC circuit. I mean, what would be the use? However, you'll definitely see RC, for example, RC circuits, which are those that require timing, such as your car's windshield wipers and traffic lights, for instance. RC circuits can also be used as audio speaker filters. You have RL circuits. They're common in RF amplifiers and DC power supplies, where the inductor in our RL circuit our inductor is used to allow DC bias current, but acts as primarily a choke or blocks, if that makes it makes for a better understanding. Blocks are RF from interfering with DC. Okay, so RL circuits are also used for low pass and high pass filters of RF. With all the vintage radios I've done, you've heard me talk about how the audio transformer is often used as a RF choke as well. And that's to clean any DC from getting across your field coil and having an effect on your audio frequencies as they're reproduced. Or RF in general as well. You want to get rid of humming, etc. But anyways, digressing again, RL circuits are also used for low pass and high pass filtering of RF. Then we have LC configurations within an AC circuit. LCs are fairly commonly used to generate high frequency sine wave signals and act as electrical resonators, establishing resonant frequencies. Now, you may also find RLC circuits. These can be fairly common within a given circuit diagram. And they're used for voltage magnification, okay? And in parallel RLC circuits used for current magnification, okay? RLC circuits can also be used as band pass filters, band stop filters, and in both low pass and high pass filtering as well. So what I really want you to understand is we begin to see how significant these passive devices are in an AC circuit. And as you spend more time working on such circuits, you begin to build an understanding of what these components are being used for in their circuit and the effect that they will have within the circuit. Then over time, it becomes a lot easier to spot them at a glance when you're troubleshooting and using a schematic or circuit diagram. And you kind of innately understand what is going on in the circuit as you view it from whatever schematic you're looking at. A bit of like muscle memory, I suppose. That being said, things do get more complex when we start discussing resonance of an AC circuit. I'm not too sure I'll get too in-depth with that and these bare bone fundamentals, but for now, we'll do a simple demonstration of one of these configurations to build our own low-pass and high-pass filter. Okay, so in our demonstration here, what we're going to do is we're going to use an RC circuit to build ourselves a low-pass filter. Okay, let me bring this down here so you can actually read this. And if you want to determine the cutoff frequency when you're making a circuit like this and establishing values for your capacitor and your resistor in an RC circuit, your formula or frequency cutoff, the formula for it is frequency cutoff equals 1 over 2 times pi times the value of your resistor times the value of your capacitor. Now, what I did to start this off was I went ahead and just selected a nominal capacitor value and the frequency that I wanted to be my low-pass filter. What is meant by low-pass filter? Well, essentially, if, say we're on a scale, here's the upper end of our scale up here, here's the lower end of our scale down here, higher frequency, lower frequency, then what a low pass filter does is at that cutoff frequency, that higher frequency, everything below it is going to be passed and everything above it is going to start to be attenuated, if I can put it relative in that terms. So what I've done, if I can get this still into the shot over here, is I wanted to establish a cutoff frequency, and I'll zoom out a tad bit here. Ooh, wrong way. There we go. And I'll move this up. I wanted to establish a cutoff frequency of something around 3,000 hertz. Okay. Typical audio transmission, some audio source be modulated onto like an AM carrier frequency, amplitude modulated onto a carrier frequency. We're talking about transmit, typical transmit bandwidth is between 300 to 3K hertz. So I just chose 3,000 hertz as where I wanted my upper limit to be, and everything beyond it to attenuate. Everything below 3,000 hertz to pass through my circuit. Okay. And so I need to get a resistor in line with my 10 nanofarad capacitor here. This is a non-polarized ceramic cap. As close to this frequency as possible. And what I determined, I did this outside of the video, just as preparatory for setting all this up, is I learned that if I was to take 1 over 2 times pi times our resistor value being a 5.6K or 5600 ohm resistor, okay, hence the color band you see right here on this resistor. I'd have to probably pull in a bit more for you to see, but, and then, well, our 10 nanofarad, so that would be 5600 times 0.000, see 1 2 3 0 0 0 1 2 3 4 5 6 0 7 1 0 7 8 9, okay, times 0 0 0 0 0 0 0 1 0. Okay, so I'm just writing this out as a decimal value. That's essentially our farad rating for this capacitor, okay, or 10 nanofarad. All right, and when you plug in these numbers, the cutoff frequency that this will come to, and I'll show you this. We'll just do a bit of math on my calculator here. Is going to be a little bit shy of that 3K mark, but 2 times pi times 600 times, here we go, 2,842 hertz. 2842 hertz. And that's pretty close. Okay. So this is going to be our low pass RC filter. All right. And so I don't want any frequency above this to really come through my speaker per se, right? I want to start attenuating those higher end frequencies. Now, ideally, in an ideal world, right? You would think that with a low pass filter, let's say we had a graph here, or this end would be voltage 0 volts to 5 volts, as you kind of see what we have up here going with our frequency, the amplitude of it, and then running horizontal. Vertical is going to be voltage, horizontal is going to be our frequency. Ideally, as our frequency increase, it should stay at a steady 5, and then right at this 2842, right? And let's see right here, if this was the mark where we hit 2,842 hertz, you would like for this just to automatically null out and go to 0. Okay, but that is not what occurs. Typically in engineering, you establish something on a Bode plot. All right. And so what we're going to find out, and we'll verify this kind of up here using our SIGGEM, is you're going to have something more akin to this, wherein your frequency comes through, right? And then once we're at that 2,842 hertz, we're going to see that it's going to start to drop just a smidge before it, all right? But then it's going to kind of round off. And with each 10 multiplier of our frequency, it's going to drop by around 10 dB or whatever. It basically gets to nothing at a higher, much higher frequency, such as like 10 or 10K or 50K or something along those lines. All right. But but we can demonstrate this. So looking at our not our SIGGEN over here on the left side, but our oscilloscope, you know, I can drop this down to 100 hertz, and we can see our input frequency coming on channel A, which is the yellow line, and our output frequency, they're roughly the same amplitude. Okay, they should be an unchanged amplitude. They're pretty much spot on, right around 4 volts. So although we see a little bit of a difference on channel 2, that is the purple channel, but essentially they're the same voltage. That's probably just due to the probe itself, or maybe a bit of compensation, something occurring there with my probe. But anyways, as we increase the frequency, you see how I have my step set to 10. We'll start to increase this, okay? And we can see that that amplitude is, man, it's staying very similar, okay? As we increase frequency, our amplitude is unchanged. Let's get up to about 1130. We see that there. I'll span out a bit. So 4.8 and 4.6, roughly the same amplitude. Okay. Now let's increase our frequency even more. Okay, we're doing that, and we're doing that. We're going to keep going, and let's get up to about. We're starting to see a difference here at around, really around 2K hertz, 2000 hertz. Let's see, 4.8 volts on our input frequency, and 4 volts approximately on outside of this filter on the back side of this. Okay, so we're starting to actually see this drop actually occur right around 2K. All right. But I mean, we're still got our frequency there, so that frequency is still going to be reproduced at the speaker. But we can see as we start going over that, look at that. We can see the amplitude on channel 2, it starts to diminish significantly. And let's get up to roughly 2,840, and we're getting 2.8, no, 3.5 volts. Hold on a second. Let's see how much of a dB difference that is. Okay, so I just pull up a voltage gain calculator online to make it slightly more simple for myself. But you can see here with a reference voltage of 4.8 there on channel 1, and we're now getting around 3.6 volts. That's almost a 2.5 dB of loss right there once we're at that that point where we need to start, attenuating. And then we're going to attenuate even more significantly as we start to increase from that point. So look, we're up to 3K now, over 3K. Let's get up to 5. And we can see with 5, and we're, let's get up to 5. So, let's see, 2.2 had us roughly here on this plot, or 2K did. 2.8 had us at like 3.6, so roughly there, we're starting to see this bell curve. We're at 5K, and 5K, we are at 2.5 volts, so 1, 2, 2.5 at 5K. Boom. So we're kind of seeing this. It's not straight. Need to put this right here, but we're seeing this kind of come down like this. Let's get up to, let me just punch in 10K. Hey, 10K. Oh, I didn't mean to mess with that. Let's not change our voltage per division. Just change the span at 10K. We'll say 10K right here. 10K, we're essentially seeing 1.6 volts. So we'll go here, put a little marker here. Now, obviously, this isn't going to be kind of bell curved like it should be because I don't have all these frequencies spaced evenly. I'm just haphazardly throwing them on a plot here. But what you can see is it's still giving us a good depiction of what is occurring. Let's go up to 20K, and you know, we're in the millivolts now. That frequency's practically not there. We're just under 1 volt or just at 1 volt. So we can say 20K, 1 volt right here. Let's do 50K. Nope, not 50. There we go. And, you know, 500 millivolts, so half a volt. I mean, and we're practically getting there close to the floor. But you can see how it attenuates, starts to attenuate before we actually get to 2.842 kHz or 2,842 hertz. It starts to attenuate there at 2,000 hertz, and then it continues the attenuation, and the higher the frequency it gets, the more rapidly that attenuation increases all the way up to, say, 50K there. And like I said, engineers typically plot this out over a Bode plot a lot better than what I've done over this video. So when you're looking at filters and stuff and you pull up the tech data on it, there's going to be some kind of plot like this on there. Okay, so this is for a low pass filter, but what if we wanted to do a high pass filter? Okay, let me reset my signal generator here. Okay, we've reset our signal generator. Well, with an RC filter, you basically just swap. Let's look at this again. Where's my card at? Oh, over here. I'm looking at my PC and I should be looking at my desktop. You swap the capacitor and the resistor in circuit, which comes first. Okay, that's how you create a high pass RC filter. All right. And so let's say I wanted to get rid of, you know, the bassy tones out of my whatever I'm producing now. Actually, in fact, I was considering doing this for my radio restorations. All right, because when I hook the speaker up to my SIGGEN, not only do I see the 60 hertz hum from my AC line, but I from those AA5 radios, but I also pull up the frequency. It's hard to get my oscope. Sorry if I said SIGGEN earlier. It's hard to get my oscope set up effectively to only see like the 1 kHz tone that I'm pushing through when I'm doing alignments, and not the 60 hertz coming from the AC hum. But if I was to establish a high pass filter, I could essentially eliminate that hum at the speaker if I was to tap off of it and create myself a little box to hook up to, and use my oscope beyond that filter I established. Obviously, the capacitor at the filter is going to have to be rated at, and I would say almost double the whatever voltage rating is coming to the speaker. So if we're seeing like 48 volts, and I'm just making something up, AC, and you know, an amplitude of that audio being amplified at the speaker, you know, I'm going to need at least a 50 volt capacitor, and then more than likely I'm going to double that to a 100 volt capacitor at whatever value I need. But again, moving on to high pass filter, I'm still going to keep something nominal, and our formula is no different. Okay, so our frequency cutoff is still going to equal 1 over 2 pi RC. All right, and what I would like to is I'd like to start that attenuation slightly higher than like 60 hertz, right? So I would say like 100 hertz is kind of where my aim is at, and then things beyond that to be below that to be attenuated. So when we talked about the low pass filter, and we said low pass, everything above this point attenuated, everything below that frequency pass through. With a high pass filter, okay, what we're saying is everything below our low frequency attenuated, and everything above it pass through. Okay, so it's the opposite, right? But so what could get us close to that with the components I have at my disposal? Again, I did this already, but I'll just work through it, right? You know, if I was looking at this formula and say 100 hertz equals 1 over 2 pi r 10 nanofarad, right? And I'd figure out my resistance value. But the one I ended up choosing was a 100K resistor, or 100, 100,000, 100K, 100,000, right? Ohms of resistance, right? And if I was to actually plug that in, 1 over 2 times pi times 100,000 times 0.123456710, or 10 nanofarad, right? Move this over 9 decimal places. But if I was to plug this in and do the math, again, I'm just going to go to my calculator. Let's do 100. Get rid of this 6 right here. And we get, this comes out to 159 hertz, okay? 159 hertz. And, you know, that's pretty close, actually. You know, slightly higher than 100 hertz. I got no issue with that. So, 159 hertz, essentially. All right. So, all we got to do is we swap our capacitor and our resistor around in circuit. And, again, so here's where I'll measure after the capacitor and then our resistor around. So why don't we do that? I am going to pull out this resistor, pull out this capacitor, and I'm going to move this capacitor up to the top here. So let's put it right here. Okay. And then I'm going to take a 100K half watt resistor, and I need to get this between ground and this point right here on my my breadboard here, and I can actually come in and should be able to measure this right here. Okay, and we're already seeing attenuation there. Let me connect my ground off. That's probably why things were acting a little bit weird. I can probably just connect this right here. Come on now. There we go. Anyways, we can already see that attenuation there at 100 hertz. So let's get above it. 1,000 hertz. And again, if we're talking about doing a Bode plot, right? Let's do 5 volts, 0 volts. Let's come out this way. We're looking at 1,000 hertz here, and we can see that amplitude. It pretty much stays the same between our input and our output, what we're measuring, all the way up to 3K hertz. You know, there's really no difference. 4.8 volts, yeah, really 4.8 volts or 4.7. But when we come down, all right, let's say that this is how am I looking at this? Well, that would be 0 here. We'll say 3K is right here. We're at 5 volts. Okay. Imaginary lines. See 1, 2, 3, 4. Trying to plot this out as best as much as possible. Let's go down to 1.5K. $1.5K, yeah, 4.8, 4.7. So, I mean, I think that's where we were pretty much at. So, we'll split the difference here, 1.5K, and we'll just say that that's still there. So, hard line through here. All right, let's take it down to, oh, wrong one. Let's take it down to 750. 750. We're starting to see a drop now, but it's very slightly. 4.8 to 4.6. Let's go just a little bit further down. Let's go to 500. Okay. So at 500, 4.8 and 4.4. So halfway through this will be 7. So we'll do 500 right here. And we'll say that 500 is, roughly 4.5 volts. And we knew that 750 was about the halfway point, was slightly starting to come down. We'll just connect those two like that. All right. And let's take it to 250. Oh, no, too far. And it's not letting me step at 250 right here. It's weird. All right, 260. 260. And you'll also notice we get a bit of a phase shift here between our input audio and our output audio. That's because of our capacitor. I'm not going to get into all that, but yeah, there will be a phase shift when you're adding capacitance. We've learned that, right? So, but that phase shift is ever so slightly. But we're, well, 90 degrees, but anyways, we're at 4 volts now at essentially 2500. So I'm just going to put a little dot here. And then we're going to see that this is going to start dropping off rapidly once we get below 150. So at 150, we're seeing 3.2. One, two, three. We'll just put that right there. And I realize my graph is probably going to be pretty hard to read here. Do apologize for that. Let's get down to 80. Ooh. Let me span in so we can see more of what we got. So 80 hertz, we're at 2 volts essentially. Move that down slightly, 80. Let's get down to 60. We're at 1.6, so just below 2. Well, you can see now how that amplitude is definitely dropping pretty quickly. And what if we get down to 10? Oh, it's like basically not even there at this point. Yeah, 400 millivolts. Right at 10, so 10. We'll just mark that down. But again, you can still see on our Bode plot, we can kind of see that that bell curve that we established with this type of this filter. Okay, so no point is it ever going to look like an exact cutoff with passive components. Okay, to say the least. But really, just for my own morbid curiosity, can I combine these two together, these two things in an RC circuit? Well, I mean, we're going to have series resistance and series or parallel capacitance or parallel resistance and series capacitance. But you know, something along those lines. So I doubt we're going to get these exact same bell curves that we had before, although crudely drawn. But maybe I'll put this all together and see what happens. Just again because I'm curious. Let's try to put these two together. Okay, so what I've done is essentially taking our 5-volt AC input, starting value 3K hertz. Now put our 10 nanofarad cap here, followed by a 100K resistor going tied to ground. And then in series with this capacitor, we got our second circuit, 2 circuits within this entire circuit, and we call them branches or whatever the term it was that we learned in DC theory. But here goes our 5.6K ohm resistor and our other 10 nanofarad capacitor going to ground. And our measuring point is going to be right here with our oscilloscope probe. This is where we'll probe. All right. And then, of course, all the grounds tied together. So we have our first probe, probe 1 input, probe 2 output. And let's see what's going to occur here. And what I went ahead and done, developing my own kind of, you know, graph here, Bode plot, is we'll look at, and you can already tell the difference right off the bat. But we'll start at 5K, okay? And at 5K, we have 1.84 volts. So we go up here, and we can probably put that kind of right here, okay? And let's go to 2500. We have 2.16 volts. So we'll put this just a bit above the 2. Now 1K, we have 2.3. So we'll put that just below midways. We'll put that right there. 500. Let's go to 500 hertz. And we're at 2.3 volts still. 2.3, 2.4. I'll put that right here. Let's go to 250 hertz. And we're back down to about 2.2. Let's go down to 100 hertz. And at 100 hertz, we are at just below 2 volts, 1.9. And let's do 50 hertz. And 1.2. 1.2. Okay. And that's where we'll just call it here at 50 hertz. All right. And let's go up to, let's see, from 5, we'll go to 10K. Change my span per division. 10K, we're at 1.2 volts. 1.2. Go to 20K. and we've got 800 millivolts, so we're below 1 volt. We're approximately right there. Let's go to 50K, and at 400 millivolts, so essentially halfway. But here we go again. We can see how this has affected our total kind of bell curve right here. Okay, so I would say somewhere between 500 to 1K is going to be our peak amplitude. So this would be about center on our filter. And then we can kind of, again, this is very askew because of how I've written this out. But I'm pretty sure if we went at smaller intervals, we would see this more as a bell curve than as a straight line through here. But we can see kind of like our around somewhere between 500 to 1K, where we're probably at max amplitude, and we establish a bell curve per se on the filter. And if you also notice, when we put these two RC filters in circuit with each other, okay, when we establish one big circuit, it actually affects the entire amplitude of our circuit because we can no longer reach up to that 5-volt source that we are initially putting in, because both of these RC filters are having an effect one on another in attenuation. So the only way to drive this frequency in amplitude upwards is to actually increase the amplitude of our input, right? But we can see how we put this in, and that establishes for us a bell curve in which we still get attenuation down on the low end, and we get attenuation up on the upper end. But is it attenuated the same down on our low end? Well, previously at 500, that's kind of askew, but I'd have to go back and watch the video, but obviously 500 is a lot different. Instead of it being just under 5 volts, we're at 2 whatever. I think 250 was right here at 4 volts. We can see that dropping down right around 50. I think we were practically in the millivolt range. I'd have to go back and watch the video, but there you go. There you have it. And that's kind of experimenting. And now, if you want to build filters with an RC network like this, there are probably better filters to do, as mentioned, especially with an RLC circuit. But yeah, you can essentially do that, and all you have to really know is, your cutoff frequency. You got a formula for that, and kind of we've established the bare bones minimum of understanding, resistance and inductance and capacitance on a circuit. But experiment between those things. Experiment with those 3 components. Plug them in, see what you come out with. This was a fun experiment for me. And kind of establishing, a low pass and a high pass filter, and, making a very crude Bode plot. And, well, hopefully you've enjoyed this part 3 of our AC series. Not sure how I'm going to close out this series yet, or what we'll move to next. We may do resonance and AC. We may not. Might do a discussion on transformers. And we'll see where it goes from there. But hopefully you've enjoyed this training video. And if you learned something and you liked it, let me know by liking the video or leaving a comment here on Patreon or over on YouTube. Again, I don't know if I may start releasing these training videos because I'm in between jobs right now. We have to move, so I do need to keep up with some content on my YouTube channel while I'm in between jobs and we're about to move to a different state. But yeah, hopefully you enjoyed this training video. Let me know. Take care and goodbye.
Mark?